So in the previous class, we learned about the associativity in cash. So so when I talked about the associativity in cash, I mentioned that in the direct mapped cache, so in the direct mapped cache, we can store only one cache line in the one set of the direct mapped cache. And then I also mentioned that because of these characteristics of a direct mapped cache, so we can waste the space of the direct mapped cache because the regulation it's kind of a regulation. So in the direct mapped cache, only one cache line can be stored in the one cache set, and then so actually this one cache set can be mapped the multiple, so and then many actually the multiple memory spaces. So the one memory chunk occupies this cache set, then and then if this other memory chunk is accessed by the load or store instructions, then this data, this occupied data, should be deleted from the cache, even though there are many empty spaces in the cache. So that is the, I said that it's the disadvantage of direct mapped cache. So we can ignore some regulations in the direct mapped cache. So we can allow the different memory spaces can be occupied in the different slots or different sets in the cache memory, this cache. Okay, so that is the fully associative cache. So actually in the fully associative cache, so this one cache set, so actually it's called it's not a set, but there is no concept of the set in the fully associative cache, but there are some better explanation. So I use the terminology set. So in the fully associative cache, the one set includes the entire cache lines. Okay, so that means if a cache has 1024 cache lines, and then in the fully associative cache, one set includes these 1024 cache lines. Okay, so that means if there are any empty spaces or empty cache lines in the fully associative cache, then this data can be allocated to any space, any empty space in the fully associative cache. But I also explained that fully associative cache is expensive compared to the direct mapped cache. So why? When the data is accessed in the cache, we just first calculate the index of cache block or index of the cache set. And then actually this index is the part of the address. So basically when the cache is accessed by the memory transfer or data transfer instructions, then the cache is also accessed by address. And then we can use the part of the address as the index of the cache, and the index is determined, then we just access a certain cache block pointed by index. Okay, so in the direct mapped cache, we can only access the one cache line or one cache block, because I said when the index is calculated, then this direct method cache only store the one cache line. So we can just access this one cache line by this direct method cache, and then we can just compare the one tag. Okay. So when I explain about the cache organization, the cache is composed of tag and data part. So in the tag, memory of the cache, the tag address and then some control flags like a valid flag or the flags are stored in the tag in the cache. And then data is stored in this data part or data memory. So when in the direct method cache, when if a set or index is computed and then selected, then we can only access the one tag to compare the if this tag include the target data. Okay. But how about the fully associated cache? We don't know the target data. We don't know where the target data is stored in the fully associative cache, because the data can be allocated to any space or any location of the fully associative cache. Then how can you find the target data? We need to compare the entire tags in the fully associative cache. So that means the fully associative cache requires the how many comparators? The number of required comparator is equivalent to the number of cache lines. So it's very, very expensive. So the intermediate form is the set associative cache. So in the set associative cache, one cache set can have up to n cache lines. So it's the n-way set associative cache. So when the set is determined by this address, then we can just select this n cache lines, so multiple cache lines within this set, and then we can just compare these n tags of n cache blocks. Okay, that is the set associative cache. So that is the intermediate form of the direct method cache and then fully associative cache. Okay, it's what we learned in the previous class, and it is also very important. Okay, so usually the commercial CPU include the set associative cache, because in the direct method cache, the cache miss rate can be high. Also, what is the disadvantage of direct method cache? The cache space can be wasted. Okay, so usually the commercial CPUs use the set associative cache because the fully associative cache is very expensive. And then also I explained that in the with a real workload or real benchmark simulation. This is the miss rate of the cache. So actually I mentioned that this is the set associativity and that this is the hit rate. So I also mentioned that the hit rate is saturated as the associativity increases. So it's not linear. It's not proportional to the n-way set associative cache. So we can select the proper associativity for the cache. Okay. So usually for our desktop or laptop computer CPU includes the 8-way set associative cache for the L1 cache, or for the L2 or L3 they include the 16-way, but it is less than the 32-way. Okay, so actually 8-way or 16-way. I think the 8-way or 16-way is the some appropriate associativity in the cache systems. Okay. Also, as the one cache set has multiple cache lines, we need to also consider the replacement policy. And then usually we use the least recently used replacement policy. So that means what is this? So if there are multiple cache blocks, so multiple cache blocks are already occupied and there is no empty space in a certain set. And then if this set is accessed by another data transfer instructions, then we need to evict the one of these occupied cache blocks. So how can we select? If this block is accessed the least recently, that means it's the oldest data, then not oldest data, it's least recently accessed. So that is it's not accessed recently. Okay, it's not accessed, it's not touched recently. So this data is evicted from the cache, and then new data is occupied in the certain cache set. Okay, that is the least recently used LRU replacement policy. And then usually this policy is used in the cache memory, but sometimes you can use the random replacement policy. Okay, and then multi-level cache. So when I first introduced about the memory hierarchy, so the memory hierarchy looks like register file, and then the multi-level of cache, and then DRAM and storage. So we can also organize the cache memory as the multi-level cache hierarchy. L1, L2, L3. So why? So I mentioned that if the memory size is large, then the performance of the memory is low because it is because of the physical constraint of the memory component. So not to understand this characteristics of the physical memory component, then you need to understand how the various IO circuit works in the real digital systems. It's very hard. So just to remember that if the memory size is large, then the performance is low. That means the latency is high. So, but we want very fast memory. So actually the register file is the fastest memory, but what's the problem? So size is very small. So then we can add the cache, like L1 cache, but if we increase the size of the L1 cache, then the performance can be degraded because it will take a long time. So usually the L1 cache size is also small, but because we want the fast memory, but if the L1 cache is directly connected to the DRAM, so main memory, what's the problem? DRAM is very slow. So, and then because the L1 cache is very small, the miss rate of this L1 cache may be high. And then if miss happens, then we need to search the data in the DRAM, and then the data will exist in the DRAM actually, usually. So, but what's the problem? Because the DRAM is very slow, the miss penalty will be very high. So what's the problem? So when you measure the performance of the memory system, we use the average memory access time. Okay, so what is the average memory access time? It's the heat time plus and miss rate multiplied by miss penalty. That's the problem. If the miss penalty is very high, and then for the error case, miss rate is also, it can be high. Okay, so around the 10% or okay. So if this for the L1 miss rate is high, but this penalty is also high. If so, the AMAT can be, oops, AMAT can be very high. If the AMAT is high, that means the performance of cache is low because it's access time. So to not solve this issue, then we can add the lower level cache. It's L2. So L2 cache is also included in the CPU package. So this is the within a chip. So that means the SRAM, L2 cache is also SRAM. Okay. So SRAM is faster than the DRAM, but the size of the L2 cache is larger than the L1. So what's the benefit? The hit rate will be higher than the L1. But as the L2 is in it's a chip package, the miss penalty for this L2 will be very low compared to the DRAM. That is the benefit of multi-level cache. Okay. So in the previous time, we quickly compared the performance of the single-level cache and multi-level cache. Okay. So in the single-level cache, the effective CPI was 9, but it is reduced to 3.4 if we add the L2 cache here. So we can also improve the performance with this multi-level cache. Okay. Okay. Then let's think about the performance of application with the cache organization. So why do we need the cache? Why do we need the cache? Not to improve the performance. And then how can we improve the performance with this cache? Because of the data used by applications exhibit will show the data locality. So that means, and then there are two kinds of locality. This is very critical. So it's very important. Okay. So what is the two kinds of locality? Temporal and spatial locality. But this locality is actually the unique characteristics of an application, right? So sometimes when we write a program or program code, then our program may repeatedly use the same data, or our program may just use the one data one time or once. So that is the characteristics of application. So for example, if we run the streaming applications such as the Netflix, maybe. So this is the kind of streaming application. So when we watch the Netflix movie, then what is the source of the data? It's an internet. And then it's like a big picture. So when we watch the streaming movie, then this data is just used once, and then it is removed from our computer system because it will not be reused even if we does not go back to the start point of the movie. So that is the characteristic of streaming data. So this kind of data is just used once, and then it is not reused. So usually the most of application repeatedly use the data. So but But what I want to say is that this data locality is the unique characteristics of an application. So this graph shows some characteristics of the different algorithm for the some different sorting algorithms. Okay. So this first graph shows the number of required instructions per item, because this is the sorting application, sort application. So you can find the different characteristics here, and then the required clock cycles per item. Also, you can find the cache misses per item. So we may think that, oh, this instructions per item or clock cycles per item is the also unique feature of the application, because better application will exhibit if there's some better characteristics for the performance of a computer system. But as you can see, application also exhibit some unique cache access characteristics. So as you can see in the quick sort, the cache misses per item is really same, but if this number of items increases and the over sum is 256, then we can see that cache misses increases linearly. How about the radix sort? It's reduced when the number of items increases, but increases, and then it's nearly the same. So the cache miss rate, where some cache misses also influenced by the characteristics of application. Okay, and then another example of this characteristic is the another example. So if we understand how cache works in the processor, then we can improve the performance of our application. How? So we learned about the memory hierarchy, but also I believe you can understand the characteristics of this high-level memory component and the low-level memory components or memories. Okay. So what is the characteristics? This is fast memory, but the size is small. And then how about this memory? So low-level memory. It's slow, but the size is large. So how can we improve the performance of application with this memory hierarchy? 어떻게 하면 되지, 진짜? performance. So if we store the data used by an application in the Aaron cache, and then if this data is repeatedly reused many times, then we can increase the performance of our application. Right. Okay, 맞습니다. 네. So I will take the example of the matrix multiplication, because the matrix multiplication is very simple. Okay. So this is the code of the matrix multiplication. Okay. So I believe everyone can understand this code because it's matrix multiplication. Okay. So how can we calculate the matrix multiplication? So C equal A multiplied by B. So in order to compute the value of this element, we need this one row, the first row of the matrix A, and then one column of matrix B. Right. then we can calculate the value of this element. Then how about this? We need the this element, this entire row of the matrix A, and next column of the matrix B. See, next column. Here, the next column. What's the problem? If the size of a matrix is large, then we cannot store entire data in level-on cache. Understand? So, what's the problem? But we know that this data of the matrix A, so let us assume that the matrix multiplication is calculated this direction, this way. Okay. So we can easily understand that for this matrix, this law is repeatedly used, right? For this matrix multiplication. Then how about the column? Column data of this matrix B. This is used. So every column is used for every computation for this row of the result matrix of C. Okay, what's the problem? If the matrix size is large, this column can be stored in the level-on cache. Also, so yeah, so we can also store the next column, column 1, column 2. But when this column is accessed, if the cache size is small, because the cache size is small, then there can be no available space in the cache. Then how the cache works for this case? How does the cache work for this case? The already occupied data, so already allocated data is evicted from the cache in order to store the new data. It's 3, 4, 5. Okay, what's the problem? The next row of the result matrix C. So we require the new row for the matrix A. How about the B? But for this element, we need the data of this row and this column. That's the problem. For this column, so we know that this column will be repeatedly used for this matrix multiplication. That's the problem. But because of the small size of the cache, even though this column will be reused, this column data is deleted from the cache. Why? Because the cache size is small. So in this case, the data for this column should be fetched from the low-level cache or memory. And it will degrade the performance of this matrix multiplication. How can you improve the performance of this application? So if the cache size is large, then we can divide this large matrix. See, if the matrix size is large, then we can divide this large matrix into the small sub matrices like this. So this is called the tiled matrix multiplication. So this is the example code of the tiled matrix multiplication. So I'll not explain about this algorithm because it's not important for this course. So if you are interested, then you can search the tiled matrix multiplication in Google. Okay. So we can. So this is some dumb matrix multiplication for the large matrices, but for these matrices, we can apply the tiled matrix multiplication algorithm. And if we use this tiled matrix multiplication, what's the benefit? So for this tiled matrix multiplication, for this element, we first use this row and this column. Here. We use this column and this column. And then for the next row, for this C, we use this row and then this column again. What's the benefit? Because the size of these sub-matrices is small, then we can store the entire data of this small sub-matrix in the Aeron cache. Okay, and then it is reused again and again for this matrix multiplication. So because so then we can reduce the miss rate. So by modifying the matrix multiplication algorithm, we can reduce the miss rate, and then we can increase the performance. So this graph shows the performance of a matrix multiplication, and then the different color represent the size of the matrices. Okay, so with the unoptimized version, that is the entire matrices are used for the matrix multiplication, but the performance is degraded as the size of matrices increases. Okay, as you can see here. But if we apply the product matrix, it's a tiled matrix algorithm, tiled matrix multiplication, then if you see some performance, then performance is nearly same or slightly decreases because the size is very large. Okay. So if we apply the some smart algorithm considering the cache organization or cache systems, we can improve the performance of our application. So you may think, oh, so actually, I mentioned that software engineers or software programmers do not consider about the hardware of hardware. So that means the CPU or CPU or processor, because it's very it's not easy. But if we, so this is some good example of the hardware, the knowledge on hardware architecture. So if we know some hardware structure or some hardware architecture of the computer system, then we can improve the performance. This is a good example. For software engineers, if we use this unoptimized version of the program, then it will be simple. But what's the problem? Performance. But if we apply to some smart algorithm or smart, if we write the smart program, then we can improve the performance. Okay, considering the hardware architecture or some hardware characteristics of the processor. So you may think that it's not important, but recently the application, the modern applications access very large data. And then the example of this large data is like big data application is the machine learning applications, like or artificial intelligence applications. So usually these kind of applications handles the large amount of very large data. It's a big data. So when this large amount of data is handled by applications, then and if we apply some optimization considering the hardware architecture, then we can improve the performance. And then it's very important actually. Okay. And then so case is done, and then I will explain. We will learn about the virtual memory. So what is the virtual? What is the meaning of the virtual? So virtual means that it's fake, that and or not real. So what is the opposite meaning of the virtual? Physical, right? So opposite meaning of the virtual memory is physical memory. So what is the physical memory? It's the real memory actually. Like a real DRAM chip or real DRAM bin in our computer system. And what's the virtual? Why do we need to learn about the virtual memory? So we are learning about the hardware. It's a physical system. It's a real system. That means the real system. It's a physical system. We are not learning about the software. But what's the virtual memory? So I will explain about the virtual memories, and then but this concept may not be easy to understand because it's virtual, not real world. But this virtual memory is the very fundamental system for the memory hierarchy. And then this techniques is actually OCP, most of the processor. So usually the smartphone processors or desktop or laptop processors use this virtual memory technology or virtual memory mechanism. Okay, so let's learn about this virtual memory. So I said that the virtual memory is the opposite concept of the physical memory. So in the memory system, so we learned that the external memory or DRAM is the main memory of the computer system. And then processor, this is the processor, access the data from this main memory, and then the data is transferred to the processor using load, store instructions. So actually, usually the data used by a certain application exists in main memory or external memory. Then what is the concept of the virtual memory? So actually the virtual memory concept was developed in order to use the large memory. So what does that mean? So when the computer was firstly developed, actually the size of the main memory was very small. So I remember that the 86 computer system is the very very old computer system, and then I believe this computer has about the I don't remember, but it's about the 40 kilobyte of memory is the main memory. So usually it's maybe, so I don't remember the exact value, but it's about the 500 kilobyte of the memory. It's very small. So usually, So think about some normal size of, size of the file. So usually, recently the size of the file is the larger than the 1 megabyte. But how about this computer? The main memory size is about it's less than 1 megabyte. And usually we actually the memory, the price is gets cheaper and cheaper. So recently we used the 4 gigabyte of the memory or 8 gigabyte, or some very good smartphone use the 6 gigabyte or 8 gigabyte of the main memory. It's very large compared to this value. But for the old computer system, the size of the main memory was very small. But if we want to use the very large memory, not very large, but it's a large memory, how can we use this large memory? By this processor. So for example, this is the size memory required by an application. But actually this computer system only has the very small physical memory, it's a real memory. Then, so I said that for this application, so we assume that every data accessed by an application exists in main memory, right? But this is the amount of memory required by an application, but this is the real memory, it's a physical memory in the computer system. How can we use this application? How can we run this application? So virtual memory concept is that, well, the size of the main memory is very small, but storage size is, the storage space is so larger than the main memory usually. So it's larger than the main memory, right? So the data used by an application can be stored in the storage. And this is because the physical memory size is small. And we can use this space like a cache. So what does that mean? If the data is accessed by this processor, then this data is moved to the DRAM. And this is accessed by an application. But some data can stay in the large space of storage. And then if this data is accessed, then this data moves to the DRAM. And then also used by an application. So this is a concept of virtual memory. Okay. So virtual memory means that so actually this is a software view, software's view. For the software, we just, the computer system provides this very large amount of the main memory. It's main memory, very large amount of the main memory. But in reality, physical, this is the software's view, but in reality, the computer system just provide the small DRAM and then some space in storage HDD, where SSD. This is the concept of the virtual memory. So in order to access the data in this main memory, so the software, then this software access the data in this main memory. So it's a virtual memory, okay? Virtual main memory with some address. Okay. But in order to access this data in the physical memory, this data should be translated into the physical address for DRAM or some location in the storage, because we don't know where data is. So data can be in the physical memory or data can be in the storage. So this address should be translated into the real address. This is the physical address. Okay. So the virtual memory concept is that for the software, the software's view, we just provide some fantastic memory. It's a large memory, and then software access the data in this virtual memory. It's a fantastic memory with this virtual address. Okay. So for example, for the software, we can provide the 128 gigabyte of the memory space. It's very large. You can use any space in this 128 gigabyte of the memory. Then software can access the data in this 128 gigabyte of the space. But in reality, our system has the 1 gigabyte of the DRAM and then 127 gigabyte in the storage. Actually, this is very small, not 128, 127. So in order to access the data in this physical system, this address should be translated the real address. So address for this physical DRAM or some location information for the space in storage. Okay, this is the concept of the virtual memory. Understand? Now, sometimes it may be difficult to understand because why do we need to provide the some virtual space or virtual memory? But it's very convenient for software engineer, because for the software engineer or software programmers, they do not need to consider about the limitation of the physical memory, right? They think that, we have a very large memory and then we can use this large memory freely. But in reality, this computer system has a very small physical memory, and then the data is the data is transferred between this small physical memory and then storage. Okay, so that is some hardware support for the software engineers. 그렇죠? 네, D램이 작으면 모든 소프트웨어가 다 이렇게 돌아요. 근데 그러니까는 버추얼 메모리라는 컨셉트는 소프트웨어를 개발하는 사람, 소프트웨어한테는 이 컴퓨터 시스템은 무한정 많은 메모리가 있다. 거의 굉장히 크니까 뭐 무한정은 아니겠지만 어쨌든 굉장히 큰 메모리를 가지고 있다. 그러니까는 메모리는 걱정하지 말아라는 컨셉으로 그러니까는 제공을 해주는 거예요. 근데 리얼 시스템은 그 리미티드 사이즈 오브 더 DRAM을 가지고 있고, 그러면 이제 남는 공간은 그냥 어차피 스토리지에 저장해서 또 쓸 수가 있으니까, 스토리지는 또 크잖아요. 그래서 1TB 이렇게 다 크니까. 물론 이제 옛날은 1TB 아니었지만 어쨌든. 그러니까 그 데이터들은 이제 스토리지에 저장을 하고 있고, 저장을 할 수도 있는 거죠. 물론 이제 굉장히 오래 걸리긴 하겠지만 데이터를 액세스를 하려면. 그렇지만 소프트웨어한테는 너는 이렇게 큰 영역, 이렇게 큰 영역을 네가 마음대로 쓸 수 있어. 이렇게 주는 거예요. 그게 굉장히 이제 소프트웨어가 프로그래밍을 할 때 여러 가지를 고려하지 않고 또 이제 할 수가 있으니까 굉장히 편해지는 거죠. 네, 이게 이제 버추얼 메모리 성능을 아니죠. 성능을 희생하는 게 아니라 소프트웨어 하는 사람한테 뭐랄까 편하게 만들어주는 거죠. 성능을 희생하진 않습니다. 그러니까 하드웨어가 소프트웨어를 서포트를 해주는 거예요. 쉽게 이제 프로그래밍이 가능할수록. 또 이제 문제가 뭐냐면은 각각의 시스템마다 피지컬 메모리 사이즈가 다를 수가 있잖아요. 다를 수가 있잖아요. 뭐 어떤 컴퓨터는 이제 1GB 메모리를 가지고 있을 수 있고, 또 어떤 컴퓨터는 이제 4GB, 뭐 8GB. 근데 만약 그렇다고 하면은 소프트웨어 엔지니어들은 어느 걸 기준으로 삼아서 프로그램을 짜야 되나요? 그거는 쉽지 않죠. 그냥 1GB만 고려를 해서 짜는 거면 성능이 떨어질 수도 있고, 왜냐면 어떤 컴퓨터는 8GB 있는 메모리가 있는데 소프트웨어가 1GB로 메모리에 맞춰서 설계가 돼가지고 내가 메모리 늘려도 1GB만 사용하는 거예요. 그거 원하지 않죠, 우리가. 뭐 이런 여러 가지 문제점이 있고요. 그렇기 때문에 소프트웨어한테는 너는 메모리는 다 쓸 수 있어. 굉장히 큰 메모리 쓸 수 있어. 라고 주지만 실제로는 그 데이터가 피지컬 메모리에 들어갈 수 있고 스토리지에 있을 수도 있고 이게 이제 버추얼 메모리의 이제 컨셉입니다. 물론 이제 실제로 데이터를 액세스를 하려면은 우리가 소프트웨어가 이제 가지고 있는 그 버추얼 어드레스 소프트웨어는 이제 버추얼 메모리 스페이스를 액세스를 해야 되기 때문에 그 어드레스는 버추얼 어드레스예요. 그거를 피지컬 어드레스로 컨버전을 시켜줘야 돼요. 그것을 하는 게 하드웨어도 하고 오퍼레이팅 시스템도 그거를 매니지를 합니다. 약간 소프트웨어랑 하드웨어랑 이제 결합되는 위치에 있는 게 이제 버추얼 메모리. 근데 그렇지만 이제 처음에 이제 시작된 거는 역시나 메모리 사이즈가 작기 때문에 그럼 어떻게 우리가 메모리를 좀 더 소프트웨어가 메모리에 구애받지 않고 소프트웨어를 작성할 수 있을 수 있을까? 거기서 이제 출발한 것이 이제 버추얼 메모리입니다. Okay. 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 So this slide summarized the concept of the virtual memory. So virtual memory is that we can use the main memory as cache. So the small main memory as a cache, and then some large amount of data can exist in the storage, like hard disk drive. So as I explained in this previous slide, so that is the start of the idea of the virtual memory. But but also I explained that with the virtual memory, the software engineer think that this computer system has very large amount of memory. So software engineers do not consider about the limitation of the physical memory if the hardware support the virtual memory concept. Okay, that is another benefit. And then the third benefit means that so actually in our computer system, multiple programs run concurrently, right? So if you check the running processes in the Windows or the Linux machine, then you can find that, in our computer system, multiple processes, many processes are running concurrently. So that means these multiple applications like a web browser, a word processor, PowerPoint, or Zoom need to share the same main memory. So what's the problem? So let's think like this. So this is the application A and application B. And then application A execute the load instruction like load x1 and then address 0x 011 0100. Right. Application B can also execute the load x1 0x 0100. Oh, it's the same address, it's the same data? No. What's the problem? Because these are the different applications. So that means different applications usually access different data. But we cannot know where data is stored. Actually, this address is determined by programmers, right? Well, compilers. So A and application A and B are running concurrently, and then with this same load instruction, try to access the same address. But we know that these two applications use the different data. How can we handle this? Actually, this address information is determined by programmers or compilers. It's not changed during runtime. Okay, so how can you handle this situation? So it's a kind of conflict. So how can we can convert this address for different location of the memory. Understand? So the same, the different application access the same address, but for this application A, your data is stored in the 0x0001. And then for B, it's a different data. So your data is in the 0x1001000. It's a different location in the main memory. So how can you access? You can just translate this address to some different location like 0x0001 is a physical address. And then, so you can just translate this address as the 0x1000. Okay, that can be possible. So what's the problem? What's the benefit? When two software runs concurrently, then the data accessed by this application can be translated into the real location of the physical memory, and then the operating system organizes some data location for this different software. And then because this address accessed by load instruction can be translated into the different physical address, the real address. That is also benefit of the virtual memory. The software engineers do not consider about this situation. A situation, two applications can run concurrently, and then two applications share the physical memory space. But if this address is firstly decided by compiler or programmers, then these compilers or programmers do not consider about this situation, the multiple process situation, because this virtual address will be translated into the physical address for the different applications. So we can distinguish this physical address pointing the different data. Okay. This is another benefit of virtual memory. So it can be a little bit tricky. 네. 이게 약간 이제 어려울 수가 있는데, 우리가 이제 피지컬과 버추얼이 이제 점점 이제 갈라지기 시작하는 그게 되는데, 약간 이제 어려울 수도 있긴 한데, 어쨌든 여러 가지 아까 제가 이제 베네핏을 여러 가지 설명했잖아요. 첫 번째는 작은 메모리를 쓸 수 있다. 그렇지만 소프트웨어는 사람한테는 너는 큰 메모리를 가지고 있어라는 착각을 줄 수 있다. 두 번째는 그 컴퓨터 시스템, 리얼 피지컬 시스템의 그런 뭐 메모리 사이즈라든지 이런 게 바뀌어도 그냥 소프트웨어는 그런 거 고려하지 않고 그냥 짤 수 있다. 세 번째는 멀티플 프로세스가 하나의 피지컬 메모리를 쉐어할 때 이런 어드레스에 대해서는 어드레스, 실제로 그 데이터가 있고 어느 곳에 있는지 이런 걸 다 뭐 고려하지 않고 그냥 마음대로 짤 수 있다. 네, 이것이 이제 세 번째의 베네핏입니다. Okay. So this is the concept of the virtual memory. So let's see how the virtual address is translated into physical address. So physical address is the real address that accesses this physical address is the real address that accesses the RAM. And what is the virtual address? This is the address used by software or application. And then this is the concept of the virtual memory. So load, the software used this virtual address for the data access or data transfer instructions like this. So this is the software's view. So software think that, oh, there are very large memory, and then we can access this data by load instruction. Okay, but this address is translated into the physical address. This is the real address. So actually, the DRAM size is smaller than this virtual memory size, and then some data may exist in the disk. So when the software try to access this data, and this data is translated into this physical address and then access this space. How about this data? We'll try to access this data in this virtual address, but it is located in the disk address. Okay, then we need to handle this situation also. 글쎄요. 지금 학생이 질문했는데, 그 어플리케이션이 같은 주소를 가지고 이제 액세스를 하려고 할 때 이게 버추얼 메모리가 있어야만 그렇게 사용할 수 있느냐? 뭐 여러 가지 뭐 아이디어를 또 낼 수는 있겠죠. 여러 가지 아이디어가 있을 수는 있겠는데, 어차피 버추얼 메모리라는 개념이 오퍼레이팅 시스템에서도 다루고 있고 하드웨어도 지금 서포트를 하고 있고요. 그다음에 글쎄요, 다른 방법이 있을 수도 있겠죠. 뭐 하면은 뭐 그렇지만은 어쨌든 지금 이렇게 쓰고 있기 때문에 버추얼 메모리를 이용해서 아주 편리하게 소프트웨어 하는 사람들이 편리하게 이제 코드를 작성을 할 수 있는 겁니다. Okay. Then so I also explain about the this virtual memory. So, and then this figure shows how the virtual address is translated into the physical address. So this is the virtual address space. So if you see the number of bits for the virtual address is about 47 down to 0. So how many bits? 48 bits. Then what is the size of this virtual address, virtual memory? So 10 bit is the kilobyte, 20 bit is the kilobyte is a megabyte, 30 bit is the gigabyte, 40 bit is the terabyte. So that means the size of the virtual memory is 256 terabyte. That is the software's view. So that means the software can use the 256 terabyte of virtual memory space. It's very large. It's nearly infinity. Okay, right? But what is the size of this physical address? So if you see that this physical address, the physical address is the 40 bit, 39 down to 0 is a 40. So what's the size of the physical memory? Each one. No. Oh, it's very large. It's 1 terabyte. It's 1 terabyte, but it's 1 terabyte of memory. Okay. But it's smaller than this virtual memory space. And how can you translate? So if we, in order to translate the virtual address to the physical memory, physical address, then we just use the mapping table. So mapping. So what's the mapping? So 1, it can be mapped to 100, 2 can be mapped to 50, 3 can be mapped to 48. Okay, that is the mapping. So if every virtual address is mapped to different physical address, then this mapping may be very complex, right? Because address 1 is mapped to 2, 2 is mapped to 100, 3 is mapped to 127. So for this mapping, the operating system or hardware need to support this every mapping information, and then that means the mapping information may occupy the very large size of the data. Okay. So for the virtual address to the physical address, we use the concept of the page. So that means we just ignore the lower 12 bit for this example. So this part is not translated, it's just directly used. So it's just actually the same for the physical address. Instead, we just translate this upper part, like 47 down to 12. So we just translate this upper part to the physical address. Okay. So that is the granularity issue. So what was this? If every byte is translated in the different physical address, then the translation will be very complex. So we just define the very large chunk, and this chunk is called the page. It's a page. So we define that it's a large chunk, and then we just translate this page number, virtual page number, to the physical page number. So with this concept, we just translate only this part, the upper part of the address to some part of the physical address. Okay. So this is the example of the 4 kilobyte of page. So if we use this page concept, the lower 12 bit is not translated. It's just copied to the physical address. We just translate the upper part of the virtual address. So in this concept, this upper part is called the virtual page number, or BPN. And then this BPN is translated into the physical page number, PPN. Okay, this is how the virtual address is translated into the physical address. So for this translation, we need the mapping information. So such as this is the BPN, and then this is the PPN, and the mapping information is the this is BPN 0, or BPN 0 will be translated 1001, 1000, 10, 2, blah, blah, blah. Like this. So this translation, so mapping information is stored in the main memory, the physical memory, and then this mapping information is actually managed by operating system. Okay, so operating system generate this mapping information. Like for BPN 0 is translated the 1000, 1010. So operating system generate this mapping table, and then it is stored in the RAM, the physical memory. Okay, so it sounds really somewhat weird. So when the load instruction is executed, and then actually this load instruction is access the data with the virtual address. And then in order to access this data, then this virtual address should be translated into the physical address, because the virtual means that it's fake. It's not real. And then real data is stored in the physical memory with the real address, like physical address. So in order to access this data, the virtual address should be translated into the physical address. How? The load instruction is accessed, then this address look up this mapping information, and then virtual address is 0. It's a physical address of 1000. And then get this physical address, and then access the data with this physical address. Okay, so this mapping information is stored in the physical memory with some table structure, and then this table is called the page table. Page table. Okay. Okay. So that's how the data is accessed in the physical memory. Okay. So virtual page number. So with this virtual page number, so we get the physical page number, and then with this physical page number, the physical memory like DRAM or some swap space in the hard disk drive. is accessed. Okay. So try to understand the concept of the virtual memory first, and then in the next time I will explain about this translation and also the cache for this virtual page table in the computer hardware. Okay? So you try to understand the concept of the virtual memory first. Okay? 네, 다음 시간에는 좀 더 이제 더 자세하게 어떻게 동작하는지, 그다음에 하드웨어가 어떻게 서포트를 하는지 좀 더 들어갈 건데, 사실 제가 이제 학생들한테 이제 설명을 하다 보면 꼭 버추얼 메모리 가면은 거의 이제 이게 도대체 무슨 소리냐, 좀 어려워하는 학생들이 많이 있는데, 버추얼 스페이스에서 놀고 있기 때문에, 그러니까는 이게 진짜 리얼한 그런 동작이 아니기, 그러니까는 리얼한 어드레스가 아니기 때문에 좀 많이 이게 감이 안 잡히는 게 있는데, 일단 지금 제가 영어로는 퀴즈에 대한 자세하게 설명한다고는 한 것 같아요. 그래서 더 이상 이렇게 하기는 좀 어려울 것 같고, 그래서 어쨌든 잘 이해를 하면 좋겠습니다. Okay. Try to understand the concept of the virtual memory, and then in the next time I will also explain about some detailed hardware support and then some detailed operation for this virtual address and the physical address. Okay. Thank you for listening. Do you have any questions? 예, 호목 3은 예, 올리겠습니다. 예, 오늘 올릴게요. So, okay. Any questions? Okay. So, okay, thank you for listening, and then see you in the next class.